going to give you a second to think about, what makes routing correct or incorrect. And then I'll ask all of you what you think. So take a minute, think about it, talk about it with the people next to you if you like. And what is the clearest way to define correct routing?
How do you tell if it works? It works. So, like, test it by sending a packet from everywhere to everywhere. Well, that's the problem. The problem is that that's hard to do, right? So there a better way of finding out just sending a packet from everywhere to everywhere.
Give you a few more seconds. All right. Anybody want to volunteer something they come up with? Anyone have an idea? Too early in the morning to be daring? All right. So I'll tell you how Scott articulated it. To foreshadow things, it turns out that for destination-based forwarding, this is the same as saying that your graph should form this, delivery tree that we talked about earlier. To see why Scott, at least I think it was Scott who formalized this, came up with this theorem, which is a single necessary and sufficient condition for validity. And so basically it says that the global routing state is valid if and only if, for all destinations, there are no dead ends and there are no loops. So a dead end is when there's no next hop somewhere. Like if a packet arrives and it's not forwarded, because there's no table entry for it. Note that the destination doesn't forward the packet, but we don't count that as a dead end because it's the destination. That's the good thing. Other hosts are also generally going to act as dead ends because generally hosts don't forward packets. Make sense? A loop is when a packet cycles around the same set of nodes. Since forwarding is deterministic and it's only depending on the destination address, if this ever happens where it gets caught in this loop, it's just going to stay in that basically indefinitely, right? So let's see if we can prove that this is the case. Starting with the necessary part. Yeah. Yes, if there's a power outage, then that could change things, but a power outage you can consider as being a dead end, right? It's going to, try to send it to the one where the power's gone out, and that's going to be a dead end. So, and this is looking at sort of, from this sort of theoretical perspective. So, I would say I would map your practical example of the power goes out and some router dies as being a dead end. Does that make sense? Okay, so the necessary part is pretty straightforward, and it's basically saying, that for state to be valid, it's necessary that there be no loops or dead ends. An equivalent statement, if you do some logic to it, I believe this is the contrapositive, says that if there are loops or dead ends, the packet won't reach the destination. And so, we can sort of show this, if you hit a dead end before hitting the destination, then you're never going to reach the destination. Obviously, right? Similarly, if a packet gets caught in a loop, because you're just going to keep looping, right? Because it's deterministic and it's only based on the destination address, which doesn't change. If you get in a loop, you're going to stay in a loop. So that's also not going to get to the destination, right? We know that the destination isn't on that loop, because if it was, it wouldn't have looped in the first place, right? It would have delivered it to the destination and then stopped. So, therefore it's necessary that there be no dead ends and there be no loops. That make sense? Okay, so the other part is this sufficient part, which is a bit more tricky. Right? And so the sufficient part says that if there are no loops or dead ends, that's sufficient to know that the state is valid. That's sufficient to know that the packet will be delivered. And so proving this, it's a bit more subtle, but assume that the routing state has no loops and has no dead ends. So therefore we know that the packet can't hit the same node more than once, right? It can't hit it twice, because that would be a loop, and I just said assume there are no loops. Similarly, we know that a packet can't stop before hitting the destination, because I said there were no dead ends, right? So that's violating this other assumption that we made. And so what's left? What's left is that a packet has to just sort of keep wandering the network, hitting different nodes. Right? Can't hit the same one, because that's a loop. So it has to just kind of keep hitting different nodes, but there's only a finite number of unique nodes in the network, right? So eventually, it's going to have to hit the destination node. So therefore, if there are no loops and no dead ends, then the routing state is valid. Does that make sense? So that sort of, showed that, this simple statement of the routing state is valid if there are no loops, no dead ends. We've sort of proven that at this point, and that tells you when packets will be delivered. So I thought now, let's see. Yeah, we've got time. So let's take a quick break, and we'll resume in maybe 5 minutes, something like that. I mean, okay. So let's get back to it. Assuming my clicker will continue working. All right, so putting it to use, verifying routing state validity. So now we've got this sort of, simple condition to check validity. So how do we use it? A couple notes first. First of all, hosts generally do not participate in routing. In the common case, hosts have just like a single link to a single router. And so they have this default route that sends everything to that router, unless they're the destination, in which case they don't send it at all. So they're not very interesting. So, we often ignore them except as destinations. Routers might be legal destinations, not just hosts, or in addition to hosts. This sort of depends on the design of your network, of your networking protocol. In Internet protocol, IP routers can be destinations, but how often have you ever wanted to communicate directly with a particular router, right? Quite probably never. So, host-to-host communication is certainly by far more common. And so we're often going to ignore the routers as destinations. But you do want to think about routers, any router, every router, as potentially being a source for packets sent to every destination, because packets may arrive at a router in sort of unexpected ways. Does that make sense? All right. So, putting our theorem to use here, we're going to focus on a single destination. We're going to ignore all the other hosts. We're going to assume all of the other routing state, except the routing state to that destination. And of course, we can do this, right, because they're all completely independent, right? I mean, it's only dependent on your destination address, and the destination address doesn't change. So if your destination address is, E, then only table entries for E matter to you. You can throw away all the other ones when you're considering this. So for each router, you're going to mark the outgoing edge with an arrow pointing at the next hop. Again, there can be only one outgoing edge at each node because we're doing this destination-based. Then eliminate all of the links with no arrows. And look at what's left. The state is valid if and only if the remaining graph is a directed delivery tree, which doesn't have any loops, right?